Hello everyone, my name is Xiaoying. I'm glad to be here to present our work CubeSense, which is a wireless and battery-free interactive sensing system based on corner reflector mechanisms. This work was done in collaboration with Zhang. Ubiquitous computing requires ubiquitous interactivity. One way to achieve it is through controllers such as buttons, sliders, and remote. These conventional controllers are either wired or powered by batteries, which eliminate flexible deployment and require user maintenance. Wireless communication techniques such as Wi-Fi or Bluetooth provide better deployability, but they often add to cost. These challenges prevent truly ubiquitous deployments of controllers and their embodied interactivities. In response to these challenges, we present a novel sensing system, CubeSense. We designed a variety of controllers which can be sensed remotely and cost only a few cents per unit. More importantly, they do not require users to exchange batteries and demand little effort to maintain. Let me first talk about our sensing principle. CubeSense is based on a special corner geometry of conductive plates, or corner reflectors, which can reflect incoming RF waves back to their sources. As we know, everything can reflect RF waves, and that is why radar can check, for example, aircrafts from miles away. But what we found particularly interesting about corner reflector is that they yield relatively strong RF reflection even with small sizes. Radar cross-section, or RCS, is a measure of the reflecting ability of objects. Corner reflectors often have high RCS, but interestingly, small changes in several factors of these reflectors will result in significant RCS changes. In our project, we take advantage of this effect and encode user interactions into the change of RCS. Specifically, we leverage four factors which include size, instant angle, material, and occlusion. To verify our sensing principle, we ran a series of simulations with CST Studio Suite. The results show that RCS continuously decreases with instant angle deviating from the board side. Additionally, larger corner reflectors always have higher RCS than smaller ones. We also found that metallic materials have much higher RCS than non-metallic ones, and RCS decreases with occlusions. Based on the principle and simulation results, we leveraged two principles in the design of these corner reflector-based controllers. In the first principle, we treat the corner reflector as a whole. In our second principle, we change only one surface of the corner reflector. To fabricate these controllers, we 3D printed their base structure out of PLA and stuck aluminum films to inner surfaces to enhance their RF reflectance. We built a proof-of-concept system with Infineon position-to-go FMCW radar board operating at 24 GHz. We built a signal processing pipeline to estimate the RCS of corner reflector controllers. We used a simple scheduling to determine discrete states such as on or off of a switch, and we use regression for controllers with continuous state. To investigate the performance of CubeSense, we ran a preliminary evaluation in an indoor environment simulating a living room setting. Particularly, we focus on three factors: distance, azimuth angle, and occlusion. Overall, we achieved an accuracy of 91.8% with discrete controllers and 73.3% with continuous ones. The reason that continuous controllers yield lower accuracies is that RCS differences between their states in the evaluation is relatively small compared with discrete controllers. We also found that the accuracy decreases slightly with distance and angle deviation. Interestingly, CubeSense can sense controllers without line of sight to some extent. CubeSense system is with limitations and in a very early stage of development. It requires much user calibration and cannot sense through thick conductive materials such as walls. We plan to leverage radar sensor with multiple frequencies and improve our sensing approach and fabrication methods. Overall, we believe CubeSense introduces a promising direction for future smart environments and ubiquitous computing applications. For more details, please refer to our paper. Thank you.